Swayam Prabha. Digital India. Educated India.
Hello everyone, let us start our course heat treatment and surface hardening. And in this course, we will be discussing the principle of heat treatment and surface hardening, as well as its thermodynamics and kinetics associated with it. And in addition, we will be also taking some engineering alloys to see that whether those principles are useful in deciding time and temperature cycles in order to have a particular material for a particular application. And we will be 2 persons taking this course. The first 10 hours of lectures, myself will continue, and then next 10 hours of this particular course will be taken by Professor Sandeep Sangal. And today is the first lecture, and in this first lecture, we will just have a kind of overview of this particular course. Now, coming to the overview of this particular course, now question arises the why we should study this course. In order to answer this why, we would like to take some examples of existing materials and let us see how we can change its properties as well as structures in order to have some particular functions to be met. And then in fact, finally, we would like to see a performance which would be sufficient to have this material in use for a longer duration without any problem. Now, whenever we talk about any material, it can be either metals or alloys, or it can be composite, it can be ceramics, or it can be polymers. Now, in this particular course, we will be mainly concentrating on metals and alloys. And whenever we talk about metals and alloys, immediately the metal and alloy which comes into our mind is steel. And in fact, if we consider the gamut of use of different materials in our engineering applications, we would see that at least 70 to 80% of applications, considering the fact that we are living in a modern society, still it is steel. Of course, there would be n number of variations in the steels, starting from a very low carbon steel to a simple mild steel to high carbon steel, and in between we have a kind of advanced steels like interfacial free steel, which is popularly known as IF steel, and then we have HSLS steel, which is high strength low alloy steel, microalloyed steels, then exotic steels like Marazing steel, which are used in very, very sophisticated applications like aerospace applications. But if we take steel, we would again see that out of all the varieties of steels, we have mild steel, which is very common, and in mild steel we generally use in structural applications. And whenever we talk about structural application, we talk about common structural applications. Now, let us say pipeline. It is a kind of variation, it is a kind of category which falls under a mild steel category. Then we have, for example, we have let us say reinforced bars. Many of those reinforced bars are mainly used under the category of mild steel. Then let us say we want to make a grill structure for our house, and that grill material is mainly mild steel. Now, that is what mild steel you find everywhere. In common applications we have mild steels. Now, whenever we talk about mild steel, then we need to see that what constitutes mild steel. Now, whenever we talk about constitutions, we talk about compositions. We talk about compositions, and if we think about iron, now steel is nothing but the alloy of iron and carbon. Now, 100% pure iron, of course, the cost wise it will be very high cost, but the application wise it will not of much of engineering use, because it cannot withstand much of load during applications. But whenever you put carbon in it, it has a positive effect of that carbon, it becomes steel. Now, where from this carbon comes, and also whenever we talk about steel, we cannot get rid of carbon fully, because the production route of steel is actually stemmed from production of iron from iron ore by the reduction process by carbon or hydrogen. You can reduce that, and then once we reduce, because that carbon is used during reduction, which is very popularly known as blast furnace process, the product is nothing but pig iron, and this pig iron is coming from iron ore and reduction by carbon, then you are getting iron plus carbon, and this carbon content would be very high. And now that is basically nothing but the pig iron, and the carbon content, it could be 4 to 5% carbon. Now, that material, the pig iron, if we have a very high carbon content, its strength, its ductility is very minimal, because it becomes a brittle material. Now, from pig iron we use steel making process to form steel. There we simply reduce the carbon content from pig iron. How can we reduce? We use oxidation process. So, the steel making process is basically oxidation process, where we oxidize carbon to reduce carbon, and that when we oxidize carbon it forms carbon monoxide or carbon dioxide that evaporates out. And in this process we definitely lose some carbon, lose some iron in the form of iron oxide, but finally the left out material is steel, where the carbon varies from 0.0022 to 0.2%, and this is in weight percent. And whenever we have carbon in this range, we call it a steel, which is nothing but the carbon iron alloy, and the carbon stays in the interstitial position. And that interstitial positions are nothing but, in crystal structure if we see, we have interstitial voids which are nothing but octahedral or tetrahedral voids, and there we have carbon. So, now we have a steel, and interestingly, if we consider the steel production from pig iron, when you are getting steel, it is oxidation process. But when we are talking about iron ore, there we are having reduction process. So, reduction process gives me pig iron and oxidation process gives me steel. Now, from this discussion, we see that composition is a factor, because if we change carbon from very low carbon to very high carbon, the difference in the properties would be, at a very low carbon, steel becomes very, very malleable. The malleable means it can be taken into form of plates, or it can be very ductile, means it can be drawn into wear very easily. And why it can be drawn into wear very easily? Because its yield strength as well as tensile strength are on the lower side, and the percentage elongation, that means when you draw it, that time the kind of elongation, uniform elongation you can provide to that particular steel would be very, very high. Now, if we consider 2%, okay, coming to this particular low carbon one, as we increase carbon content, its strength increases, but consequently its ductility decreases. So, that means it becomes more and more harder and harder, but its ductility becomes lesser and lesser. So, that means we have some variation in properties with the function of carbon content. Now, whenever we have different percentage of carbon content, at the same time we also come across other alloying elements during the processing of pig iron as well as iron ore, and which leads to manganese or silicon content in the steel. So, mainly if we consider mild steel, the mainly we have carbon, manganese and silicon, these three elements. Carbon generally in case of mild steel, its maximum, its 25% is 0.25% carbon. Manganese, it can be 0.5 to 0.8%, silicon could be 0.2 to 0.3%. Depending on different varieties, this material can vary much, but can vary little, but this one always stays around 0.25. If it is more than 0.25, that will not come under the category of mild steel. So, if we take 0.25% carbon maximum, we can term it as mild steel. If we at the same time we do not have much of other alloying elements like vanadium, titanium, chromium, all sort of stuffs. Those are costly alloying elements. Now, when we talk about these alloying elements, forget about these other alloying, and of course, there will be sulfur, phosphorus, but we always take care of the sulfur and phosphorus. We try to maintain this composition of phosphorus, concentration of phosphorus and sulfur to be minimum, because those elements are not beneficial elements in terms of properties we want from this particular steel. Now, coming to only carbon, if we let us say 0. carbon percent, and then we try to see what sort of structure it generates, we can easily come to know from a particular pictorial graph which is called phase diagram. Phase diagram is nothing but the equilibrium diagram of different phases appearing at different temperature, and if we change the composition, and this phase fraction would change as well as different phase might appear. Those phase diagram part we will talk in third lecture, but if we consider these particular composition part only, and this composition part if we consider, we can see that if we change composition, we can change its properties. We are getting little bit of idea from this composition. So, composition is one of the major factors we must consider. Okay. So, now coming to whenever we talk about a material, we let us first see what are the parameters we should look at in order to see whether we need time temperature variation to get a different properties or not, whether we would get it or not. Now, from this discussion it is very clear that composition is a factor which controls, from our discussion it is very clear that it controls the properties, but at the same time it also controls the structures. For example, if we consider 100% pure iron, if we can make, okay, which is very difficult to form, 100% pure material is very difficult to form, which will come across during a thermodynamic consideration of alloy formation, you would see that it is extremely difficult to form 100% pure material, because the culprit is nothing but entropy part. The entropy of mixing disallows us to form 100% pure material. Okay. But if we, for example, let us say 0.0001% carbon steel, which we can consider as a pure iron, and in the pure iron we have some structures, and these structures could be either it could be macro structures, it could be microstructures, it could be crystal structures. Now, different structures, there would be other structures also. We are not getting into the atomic structures, because iron, pure iron is also consisting of huge numbers of iron atom. We are not going into that iron atom, because we would be only concentrating on these particular two structures, and this macro structure sometime would be very important when we talk about a surface preparation, that would come in the macro structure group. And whenever we talk about different structures, if we consider these two can be considered as a structure which can be seen in naked eye, that we can consider as a macro structures, naked eye, and the magnification we can go up to, let us say, 10 to 20x depending on the power of the human eye. But whenever we talk about microstructure, some structure it will be inherent in this particular, in any material, and that structure we cannot see with the naked eye. We need microscope, and that microscope, it can be a very small magnification. Small magnification, I mean to say 50x, that means we can blow it up by 50 times, or it can be a very high magnification, we can blow it up to 1,000,000 times. Okay. That means we have entire range of microscopes. For example, optical microscope, where we can go up to 2000x, that means 2000 times we can blow the material, blow it up, or we can use a sophisticated transmission electron microscope. We popularly know it as TEM, okay, transmission electron microscope, where we can go 1,000,000 times. Now, this microstructure changes with composition. At the same time, crystal structure also changes with composition. For example, if we take pure iron at room temperature, the pure iron structure is BCC, which is nothing but body centered cubic, body centered cubic. Now, if we take this pure iron temperature to more than 910 degrees Celsius, we have a different structure. What that structure is called FCC, which is called face centered cubic. Face centered cubic. Now, these are the two basic structures what we have in pure iron. There is one more structure which is called BCC again, but that forms beyond a temperature of 1395 degrees Celsius, which is called again BCC. Now, the question is, which is again body centered cubic, but if we consider room temperature below 910 degrees Celsius, we have BCC, that time it is called alpha, and this time which is beyond, which is called delta beyond 1395 degrees Celsius. And this one appears between 910 degrees Celsius to 1395 degrees Celsius, if we consider pure iron. Now, whenever we talk about these structures, we must consider that these are solid state structures, as well as during that time we are fixing the pressure at 1 atmosphere. If we change the pressure as well as temperature, we can come across other structures as iron, which could be HCP also, which is called hexagonal close packed structure. But for our application, we would be happy with these BCC and these FCC. Classic example, mild steel, if we consider the iron what we see, that is nothing but the BCC, and stainless steel, or the popular stainless steel which is called 18-8 stainless steel, 18-8 stainless steel, where 18% is chromium, 8% is nickel. So, the stainless steel what we see in our common application, for example, wash basin is a classic example of 18-8 stainless steel. So, there we do not have stain, and in case of stainless steel, the stain is nothing but the rust, because iron always forms rust if it comes into contact with moisture as well as oxygen, and that too are amply available in environment. So, if we have moisture as well as oxygen, then they can form rust, which are nothing but again iron oxides or hydroxides. But in case of 18-8 stainless steel, we do not form those oxides or hydroxides. That is why the surface remains very shiny and it does not corrode. Okay? So, there is a term called corrosion. The corrosion does not happen in case of 18-8 stainless steel. So, that is what it is called stainless, there is no stain. Now, in this case, the structure is nothing but gamma, which is nothing but FCC, which is also called gamma phase. So, that means we see in case of pure iron, if we change the temperature, we are coming across different structures, which is nothing but the crystal structures. Now, if we try to see the microstructure, in case of pure iron, the microstructure, if we consider BCC microstructure, the microstructure contains like this, which are the grains of alpha, and these are grain boundary. So, this kind of structure we would see if we see under a microscope. But how can we see under a microscope? We have to polish it, and polish it in such a way that we can see our face on the surface of that polished surface, and then we have to etch it. Etch is nothing but the electrochemical reaction with an acid, which is normally used nitric acid. That acid solution we call it nitrile, and that nitrile, if we dip that particular polished surface, mirror polished surface, and then allow it to react for some time, and then if you take it out and see under an optical microscope, you will see a grain structure like this. So, these are called grains of alpha, and then these are called microstructure. Okay? So, now that means we see crystal structure, we see microstructure, and now we see that if we change composition from no carbon to a little carbon, here the carbon content is of the, for example, in case of 18-8 stainless steel, carbon content is 0.8%. If we take a commercial stainless steel, so if we see that with a little carbon content, but if we increase the alloying elements, that means if we change the composition, we can see that our structure changes from BCC to FCC. that means, as we have told that if we change the composition, we can have change in structures. We can see the change in structures means change in crystal structures. And now, when we change the composition from gamma to alpha, the microstructure would be almost similar like this, but only thing it will change to gamma. So, the microstructure almost remain same, but the crystal structure changes from alpha to gamma. So, that means we see that the composition is one factor, as well as there is one factor which is intricately associated with the composition, that is called structure, and that structure could be crystal structure or microstructure. We can change both depending on the change in composition. Okay. So, let us stop here for the first lecture, and we will continue this topic in our second lecture. Thank you.